Out there in the vast expanse of the cosmos, there exist objects so extreme, so mind-bogglingly dense, that they challenge our very understanding of physics. These objects are not just fascinating, they are essential to our comprehension of the universe. They push the boundaries of what we know about matter, energy, and the fundamental forces that govern the cosmos. These objects are neutron stars, the remnants of massive stars that have lived a life of cosmic extravagance and met a spectacular end. When a star much larger than our sun exhausts its nuclear fuel, it undergoes a dramatic transformation. Imagine a star, much more massive than our sun, reaching the end of its life. Over millions of years, it has burned through its hydrogen and helium, fusing these elements into heavier ones like carbon and oxygen. This process releases an immense amount of energy, which counteracts the force of gravity trying to collapse the star. But eventually the star runs out of fuel. It has burned through all its fuel, and its core can no longer withstand the crushing force of gravity. The outer layers of the star are blown away and the core collapses under its own weight. The core collapses in on itself, squeezing the star's matter into an incredibly small space. This collapse is so intense that it forces protons and electrons to combine into neutrons, resulting in a star composed almost entirely of neutrons. This collapse is so violent that it triggers a supernova, a catastrophic explosion that outshines entire galaxies. The energy released in a supernova is so immense that it can briefly outshine an entire galaxy, releasing more energy in a few seconds than our sun will emit in its entire lifetime. And what remains after this cosmic cataclysm? The outer layers are expelled into space, creating a beautiful nebula while the core is left behind. This remnant is what we call a neutron star. A neutron star, a sphere so dense that a teaspoonful of its material would weigh billions of tons on Earth. To put this into perspective, imagine compressing the mass of the entire human population into a single sugar cube. That's the kind of density we're talking about. Neutron stars are not just incredibly dense, they are also incredibly hot, with surface temperatures reaching millions of degrees Celsius. This heat is a remnant of the supernova explosion and the intense gravitational forces at play. But what makes them truly remarkable is their spin. When the core of the star collapses, it retains its angular momentum, causing the neutron star to spin at incredible speeds. Some neutron stars, known as pulsars, spin hundreds of times per second, making them the fastest spinning objects in the known universe. These pulsars emit beams of radiation from their magnetic poles, and as they spin, these beams sweep across space like cosmic lighthouses. When these beams point toward Earth, we detect them as regular pulses of radiation, hence the name pulsar. The study of neutron stars and pulsars has provided invaluable insights into the nature of matter under extreme conditions, the behavior of magnetic fields, and the fundamental properties of space and time. They serve as natural laboratories for testing the laws of physics in ways that are impossible to replicate on Earth. Observing these enigmatic objects requires sophisticated telescopes and detectors, often located in remote areas far from the light pollution of cities. Radio telescopes in particular are crucial for detecting the faint signals emitted by pulsars. As we continue to study neutron stars, we uncover more about the universe's most extreme environments. These discoveries not only deepen our understanding of the cosmos, but also inspire new technologies and methods for exploring the universe. In the grand tapestry of the universe, neutron stars are among the most fascinating and mysterious threads. They remind us of the incredible forces at work in the cosmos and the endless possibilities for discovery that lie ahead. To understand how neutron stars form, we need to take a journey to the heart of a dying star. This journey takes us to the final moments of a star's life, where the most dramatic and violent processes in the universe unfold. Stars are giant nuclear furnaces, fusing hydrogen into helium in their cores and releasing tremendous amounts of energy in the process. This fusion process is what makes stars shine so brightly in the night sky, and it is the source of the light and heat that we receive from our own sun. This energy, in the form of radiation pressure, pushes outward, counteracting the inward pull of gravity. The balance between these two forces is what keeps a star stable for most of its life. The outward pressure from the fusion reactions in the core supports the star against the crushing force of its own gravity. For millions or even billions of years, these forces remain in balance and the star lives on. During this time, the star goes through various stages of its life cycle, burning through its nuclear fuel and evolving in size, temperature, and brightness. However, This delicate balance cannot last forever. As the star ages, it eventually exhausts the hydrogen fuel in its core, leading to a series of complex and dramatic changes. Eventually, the star exhausts the hydrogen fuel in its core. When this happens, the core contracts and heats up, causing the outer layers of the star to expand and cool. This phase is known as the red giant phase, where the star becomes much larger and more luminous. Without the outward push of nuclear fusion, gravity takes over, and the core begins to collapse. The core's collapse is a rapid and violent process, leading to the formation of heavier elements through further fusion reactions. For stars much more massive than our Sun, this collapse is catastrophic. The core's collapse is so intense that it triggers a supernova explosion, one of the most powerful and energetic events in the universe. The core implodes in a fraction of a second, reaching unimaginable densities and temperatures. The implosion generates shock waves that travel outward, causing the outer layers of the star to explode violently. The implosion sends shock waves through the star, ripping it apart from the inside out. These shock waves carry away the outer layers of the star, leaving behind a dense and compact core. This is a supernova, one of the most energetic events in the universe. The explosion releases an enormous amount of energy, outshining entire galaxies for a brief period, and creating a spectacular display of light and color. And at the heart of this cosmic explosion, a neutron star is born. This remnant is incredibly dense, with a mass greater than that of the Sun, but compressed into a sphere only about 20 kilometers in diameter. Neutron stars are fascinating objects, with extreme magnetic fields and rapid rotation rates, making them some of the most intriguing and mysterious objects in the universe. Not all neutron stars are created equal. These remnants of massive stars that have exploded in supernovae are incredibly dense and compact, often packing more mass than our Sun into a sphere just a few kilometers across. Some, known as pulsars, possess a remarkable property. They emit beams of radiation from their magnetic poles. These beams are not constant, but instead flash on and off as the pulsar rotates, creating a pulsing effect that can be detected from Earth. These beams, like beams of light from a lighthouse, sweep across space as the pulsar rotates. Imagine a cosmic lighthouse, its beams cutting through the darkness of space, signaling its presence to anyone who happens to be in the path of its light. If Earth happens to lie in the path of one of these beams, we detect a pulse of radiation, hence the name pulsar. These pulses can be incredibly regular, with some pulsars acting like the most precise cosmic clocks known to science. The discovery of pulsars in the 1960s was a major event in astronomy. It all began when Jocelyn Bell Burnell, a graduate student at the time, noticed a series of regular radio pulses while analyzing data from a radio telescope. At first, some scientists even speculated that these regular pulses of radiation might be signals from extraterrestrial civilizations. The regularity and precision of the pulses were unlike anything seen before, leading to the initial nickname LGM for Little Green Men. However, it soon became clear that pulsars were natural objects, albeit ones with extraordinary properties. These rapidly spinning neutron stars were a new class of celestial objects, providing insights into the life cycles of stars and the extreme conditions in the universe. The rotation of a pulsar is not just a curiosity, it is a key to understanding these extreme objects. The spin rate of a pulsar can tell us a lot about its age, its magnetic field, and the environment in which it formed. By measuring the rate at which a pulsar's pulses reach Earth, astronomers can determine its spin rate. This information helps scientists to map out the pulsar's history and predict its future behavior. And some pulsars spin incredibly fast, hundreds of times per second. These are known as millisecond pulsars, and they challenge our understanding of physics with their extreme rotational speeds and the forces at play within them. The study of pulsars continues to be a vibrant field of research. Each new discovery adds to our understanding of the universe, revealing the incredible diversity and complexity of the cosmos. From their discovery in the 1960s to the present day, pulsars remain one of the most fascinating and mysterious objects in the night sky. As we continue to explore the universe, pulsars serve as cosmic lighthouses, guiding our way through the vast expanse of space and time. They remind us of the incredible power and beauty of the cosmos, and the endless possibilities that await us in our quest to understand the universe. Imagine an object the size of a city spinning so fast that it completes hundreds of rotations every second. That's the reality of some pulsars. These objects, born from the death throes of massive stars, spin at speeds that defy our everyday experience. The fastest spinning pulsar known, PSRJ 1748-2446 AD, whirls around at a mind-boggling 716 times per second. To put that in perspective, imagine a point on the equator of this pulsar. That point is traveling at about 24% the speed of light. These incredible rotation speeds are a testament to the extreme physics at play in neutron stars. But how do pulsars achieve these incredible spin rates? The answer lies in the conservation of angular momentum. Just like a spinning figure skater spins faster when they pull their arms in, a collapsing star spins faster as its core contracts.